my name is Clifford Anderson, and welcome to Claire's Chemistry Corner. Today we're going to get down to business to defeat some Huns, because we're going to we're going to talk about nuclear chemistry today. Heck yeah. I got a test on this tomorrow, so really I'm just doing this video to study, because honestly making these videos helps me maybe more than it helps you guys. I don't know how much it helps you objectively, but who knows. So anyways, so what we're going to talk about first is we are going to talk about what exactly is radioactivity, what makes something radioactive, what makes an isotope radioactive versus non-radioactive, versus stable, and the different types of decay that an isotope can do, which is pretty chill. So yeah, let's just start off with what exactly is radioactivity. So radioactivity is basically, like, long story short, too long, didn't read, is when an isotope releases energy / particles that are charged with energy that causes the exposure of film. And if you guys have gotten to this in chem, it was what the Curies did, is what the Curies discovered. They the Curies radiated their way to history. The decay of rocks around them happened for eternity. Oh, teach me more about atomic life. Please won't you tell me more? I love that song. I sing that song all the time. In the car, in the shower. It's great. It's great. Classic tune. Anyways, yeah, so that's basically what they discovered. It was pretty chill. Marie Curie is a home dog, so yeah. So yes, so what is radioactivity? An isotope that is releasing energy or particles charged with energy that causes the exposure of film. So that means the little spots on the film will show up, and that means that stuff is coming out of the nucleus. So other ways you can tell without poisoning yourself and giving yourself cancer are looking at the binding energy of the nucleus, which can be found with the delta E equals delta mc squared equation. Which will all sound super smart if you'll, like, just rattle off, just rattle off that one. What's the answer to all the test questions? Delta E equals delta mc squared, and you'll just look like a freaking genius. So yeah, so basically the higher the binding energy is, the more stable your isotope is. I like to think of it as Gorilla Glue versus Elmer's. My chem teacher talks about it like this, but if you have Gorilla Glue in your nucleus, it's more tightly bonded, right? Versus Elmer's glue, it's more loosely bonded, and things are likely to fall out, and things are likely to be spit out of the nucleus in a radioactive sense. So if you're using Gorilla Glue, it's a lot more tightly bonded, and things aren't going to just spit their way on out of there. They are not going to spit fire. Like I do on my mixtape, dropping September 13th, 2015. I am so sorry. Okay, anyways. You know, I should really edit this video, but I'm too lazy for that, so this is the one cut that I'm gonna make, and so y'all get in all the glory. Number 2. You can look at how many protons are neutrons, or how much junk is in the nucleus. And if there's too much junk in the trunk, then it wants to get the junk out. So basically that means that any isotope that has an atomic number or proton count greater than 84 is most likely going to be radioactive. And we call these big mamas. Yes, we call them big mamas. Get used to it. And these big mamas tend to be alpha decayers, simply because they are so big, and when you have that much junk in the trunk, you want to get the most bang for your buck in getting the junk out. You want junk economy. You want to get the biggest junk out. So what they spit out is an alpha particle, which is your run-of-the-mill helium nucleus, which is mass number 4, He, atomic number 2. So that is an alpha decay, so a big mama spits out another big mama. That's just how I like to remember it. And then number 3, what you can do is you can check out your handy-dandy stability graph. A stability graph is an exponential increase, and anything on the line is going to be stable. The line ranges from proton to neutron ratios from 1 to 1, which means they have the same number of protons as they do neutrons, to 1.5 to 1, which means that they have a 3 to 2 ratio of protons to neutrons. So if your specific isotope is on the line, then you're all set to go. It's stable. If it's not, it's radioactive. So, my grandma's texting me. I got cough drops. Okay. So let's talk about modes of decay. So a radioactive isotope can decay in, I think, about 4 ways. It's 4 ways, at least that we've learned about. Number 1 is alpha decay, which is big mama spitting out a big mama. So when you have a big mama, it spits out a alpha particle, which is a helium nucleus, as I just mentioned. So it will be its bad self and spit out a helium nucleus, and that will create a new atom plus energy. And you have to put the plus energy at the end because that's basically like the essence of nuke, is that you create energy, because that's how nuclear power plants work, and that's how nuclear bombs are made. Cool. A little fun fact for ya. Number 2 is beta decay, which is really common in the smaller mamas, the mamacitas, which is really common in the smaller mamas. And in this one, what happens is a neutron in the nucleus croaks. It's gone kaput, bye-bye, and in its place, a brand new proton and electron are created, because it's theorized, like, it's pretty much been proven, but it's technically still a theory, that a proton and electron come together to create a neutron. So when a neutron croaks, its parts are going to be spit out, so it creates a new electron and a new proton. So basically what this means is that the mass number stays the same, but the atomic number increases by uno. So that's pretty chill, I guess. I don't know, that's kind of cool. And then number 3 that it does, which is my least favorite one, I hate this one, it's positron emission. And a positron is an extremely small mama. It's like a mamacita, because it has barely any mass. And a positron is basically the same thing as an electron, but it has a positive charge. So I'm like pick a side, buddy. Like, okay. So it's basically an electron, but with a positive charge. And in positron emission, what happens is a proton is toast, gone. So basically how the reaction goes is you have a proton, which is your single helium nucleus, so it's 1H1. You said your hydrogen nucleus, it's your hydrogen nucleus. Also, not a helium nucleus, it's a hydrogen nucleus. So 1H1 spits out a positron, 0E1, not 0E negative 1, because that's an electron. 0E positive 1, because it's a positron, plus a neutron. Yeah, so it's a positron plus a neutron, and that's pretty chill. So if you're writing this in a reaction, like I have one on a quiz I just took, let's see, what one did I have to do? I had to do one for yttrium 85. So 85, yttrium 39 is the atomic number, would then spit out a positron, so 0E1. So your mass number would stay the same, so the new element would have a mass number of 85, because 85 plus 0 is 85, and you know how both sides have to balance. And because there was a positive 1 on the electron, the new atom has to have a mass number that is an atomic number that is 1 less than yttrium does. So yttrium, because yttrium has an atomic number of 39, the new element is going to have an atomic number of 38. So it would be strontium 85. And this all adds up if you go back through, because 85 plus 0 is 85, and then 38 plus 1 is 39. So because both sides of the equation have to balance out, it'll balance out. And don't forget your plus energy at the end, because you have to do that. And then the last thing that we're going to talk about, wow, this video is long. Okay, and the last thing we're going to talk about is K capture, which is my favorite one. Not for morbid reasons, like, this is gonna get pretty morbid, but I just think it's kind of cool. So anyway, so K capture is basically electron suicide. It is when an electron falls into the nucleus and bonds with a proton because, you know, opposites attract. Although that's not true in dating. Do not. That's a bad choice. Bad choice. I digress. Anyways, so electron suicide is when an electron goes into the nucleus. It just kind of falls in there. Bay caught him slipping, and it just falls in there and bonds with a proton and creates a neutron. Because an electron and a proton make a neutron. So, but the electrons that are most likely to do this are at the lowest energy level, and if you want to keep being morbid, you can think about it like this. The most depressed people often have the lowest energy levels. That's scientifically proven. The most depressed people often have the lowest energy levels, so they are the ones most likely to fall in. This just got really sad. I feel like I need to put the links to the suicide hotline in this video. If anyone needs any help, they can come talk to me. Please, I'm very loving, and I don't want any of you to be mean to yourselves because you're all wonderful. Okay? Okay. That was a good pep talk. So anyways, yeah, so the electrons that are most likely to fall in are the electrons on the lowest energy level because those are the ones that are closest to the nucleus and most likely to be sucked in by a proton. And you may recognize this a little bit because it is backwards beta decay. So instead of an electron being put out, an electron's being put in. So that's pretty cool. I hope you guys found this interesting. This was definitely more geared towards AP, so I'm really sorry, Gen Chem. But you guys will learn this stuff too. I mean, you'll go over all this stuff. It was just kind of assuming that you know some things that you maybe don't. But if you do, heck yeah. So yeah, if you guys are taking the nuke test tomorrow, Godspeed, and I will catch you on the flip side.